Okay, so 7.5 is going to be differentiating logs. Okay, so we will do differentiation and then integration. Integration will be 7.6, which we'll do on Friday. Okay, so the nice thing is that they kind of separate this into two sections because it's kind of a lot of stuff to absorb. So the reason that they come up with these derivatives, okay, we are basically taking the derivative of a natural log, goes back to section 7.3. Okay, so if you wanted to turn back in section 7.3, you would see this little formula, okay, and you'd realize, oh yeah, natural log, the inverse of natural log is the exponential function, okay, which is right here. And so basically what it ends up going into is this piece right here. Okay, so if we're deriving the natural log, you end up with 1 over the derivative of the natural log. And what happens if you simplify e to the natural log of x? It becomes x. Okay, so that's basically how they ended up concluding this idea. And it's not imperative that you understand why. It is more important that you remember this definition. Okay, so I did write these down on your little note sheet. Okay, so we're basically looking at, let's see, specifically number 9, number 10, number 11, and number 12. So maybe what you might want to do is add little notes onto your cheat sheet if that is helpful for you. Okay, so number 9 is very basic. It is simply a straight up derivative. But number 10 is slightly different. What do you notice about number 10? It's kind of different than what we've seen in the past. So like if you look at your rules for 6 and 7, so kind of like what Tyler did on the warm-up, on the chain. Remember that he did the chain, he added 1 to the exponent and then he divided by it. So this one is like, notice that the derivative goes up on the top and then the piece of the log, whatever it happens to be, goes on the bottom. So in my mind that feels opposite, but that is the correct way, so just try to remember that. Okay, so that's if you're in a natural log, and then 11 and 12 are if you're doing an log log with any base. Okay. Ready? Here we go. So number 1 I mean, is the natural log of 5x. That's where I got the 5 from. Which rule am I using? 9, 10, 11, or 12? Close. What? It's in between those two. Number 10. Okay, so you know if it's a natural log, you're either using number 9 or 10 because it's an ln, literally. That's a 9 or 10. Okay, the next thing you have to decide is, am I doing it of x or is it something other than x? So if it's something other than x, that's a number 10. Okay, so I'm just going to do the derivative on the top divided by what the natural log is of. So what is number 1 going to become? So what's the derivative of 5x? 5. Okay, and then I divide by the 5x, and if I simplify that, what does this become? 1 over x, which is kind of an interesting thing, that would really be the same as if we took the derivative of the natural log of x. Okay, so something to kind of notice. Okay, what about number 2? Number 2, which rule are we using? What? Number 10 again, good. Okay, so I just put the derivative on the top. What's the derivative of 3t squared minus t? Okay, good. 6t minus 1, and then I just simply divide by 3t squared minus t. What do you guys think so far? Good? Check. Okay, what about number 3? X times the natural log of x. How would you derive that one? Okay, you're going to have to use a rule that you've used before today. You have to do the product rule. Okay, this is product rule because I have two x's involved. Okay, so I have the x is my first and the natural log of x is my second. Okay, so I have first d second plus second d first. So first, what's my d second? What's the derivative of the natural log of x? Good. Plus the second, which is the natural log of x, d first. What's the derivative of x? 1. Good. Okay, so what is x times 1 over x? 1. Good. So it just becomes 1 plus the natural log of x. Pretty easy there. Okay. All right, so example 4 kind of explains something about the absolute value of x inside the natural log. Okay, so they ask you to graph the natural log of the absolute value of x. So if I was going to just draw the natural log of x, what does the natural log of x look like? We did this in the last section. What does it look like? Has a vertical asymptote where? At 0. Where does it cross through the x-axis? 1. Okay, and you can even go even more specifically that it's going to cross through the point E1. So that's like there-ish. Okay, so remember, if I have absolute value on the inside of an x, what does that do to my function? How do I draw it? You reflect it over the y-axis exactly. So anything that's on the right side is simply reflected, which, since there isn't anything on the left-hand side, that makes it very simple to reflect. Okay, so this is your, that doesn't look good, but okay. Your natural log of the absolute value of x. So it says, for the right half of the graph, the absolute value has no effect. Okay, so the derivative of the natural log of the absolute value of x is 1 over x. So that's that highlighted piece. So literally, if the absolute value you can kind of ignore it, and it just is the 1 over x. So all of those rules that you learned above are going to apply. Okay, so moving into this little piece right here. What is the, well, I guess that they kind of already said that. No, they didn't. Yeah, they did. So if I just go from here to here, right? The derivative of the natural log of the absolute value of x is 1 over x for that. Okay. What's that? It's x plus. Right. Exactly. So they're saying, so basically what it's going to say is it can be for x is less than 0, or it can be for x is greater than 0. So they're just kind of pinpointing on the left side, but it's going to hold true for both sides. Nope, it's still going to be a positive. It's going down. Yeah, I see what you're saying. Yes, it does make sense. Undifferentiated absolute value can be ignored, but it should be a positive. But I see why you would say that. The left side looks negative, yeah.
It would just be negative. Negative wherever you check on both sides, the slopes are just
Yeah. So I kind of feel like their explanation makes us more confused now, because it should be a positive. But I'll look into that, and let's just pretend that it's a positive, and then I'll clear it up later. So let's go ahead and do number 5. Okay, so of our little rules, we have the natural log of the absolute value I do want to highlight this little thing. The absolute value can be ignored. Okay, so that's the idea of this, is that we can ignore the absolute value piece and just derive it as if it was the quantity of 5 minus 2y cubed. Okay, so which rule are you using for number 5? 10 again. Okay, so we're going to derive the inside. So what's the derivative of 5 minus 2y cubed? Negative 6y squared. And then divide by 5 minus 2y cubed. Fair enough. Should we check that on the Inspires? Or do you guys, okay, you're feeling good? Maybe I will later and just be 100% sure. Okay, so question number 6. Now this is the type of question that you're totally going to see on the test. Okay, it looks incredibly complicated. And the first thing they do is they ask you to rewrite it. Okay, so for you to do this problem, you have to not only understand how to derive a natural log, you also have to understand the properties of logs. Okay, so if you're thinking about the last section where we expanded, what would this natural log expand into? Plus, can I go ahead and say 1/2 since you said square root and put that in the front? Natural log of 2x plus 1. Okay, then what? To get that quantity in the bottom. Minus, good. The natural log of x squared plus 1. Okay, so does everybody follow that expansion using the properties? That's a power property rule. So yes, usually, but by the power property, when you expand it, you just take that exponent and put it in the front. So they're equivalent. Okay. So now the nice thing is about the standard form is now you can just use, you can integrate each term individually and use our little rules. Okay, so what is the natural log of x? 1 over x. Okay, then I have 1/2 times the natural log. I'm going to pull the 1/2 off and then just multiply by the derivative of the natural log of 2x plus 1. Okay, so that's another rule, 10. Okay, so what's the derivative of 2x plus 1? 2x, and then over 2x plus 1. So that's the derivative of that. 2. Yes, thank you. Good catch, good catch. Thank you. Okay, then minus, what about the natural log of x squared plus 2? What's the derivative of x squared plus 1? 2. There it is. I knew there was a 2x in there. Over x squared plus 1. Okay, so then you would simplify this as far as you possibly could. The only thing that I see that can simplify is the 2's on that second term. So I would leave this as, whoops, not equals, less plus 1 over 2x plus 1 minus 2x over x squared plus 1. So I would assume that's what the calculator would show as the solution. Okay, good on that one? That one's not too bad as long as you understand the expansion. Okay, number 7, this one is interesting, and it took me a little while to get there, and then once I figured it out, I was like, oh, duh. So they use the change of base formula. Okay, so if you flip over to page 150, you can see the change of base formula. Okay, so they give you the change of base. I'll just write it here so you don't have to flip. So if you have the log of base a of x, that's equivalent to the natural log of x over the natural log of a. So they always like you to use like the most simple form, so they prefer the natural log piece. Okay, so if I take that and rewrite my derivative piece to show that the derivative of the natural log of a of x is equivalent to that other side, I would have d dx of the natural log of x over the natural log of a. Okay, so how would you derive this? I know what the answer is, but I want to prove that it's true. Okay, so remember that a is some constant value. It's important for you to remember. That's what took me so long to figure this out. Okay, so what you can do is you can separate this, d dx. So then you have 1 over the natural log of a times the natural log of x. Okay, so 1 over the natural log of a is a constant number. Okay, so imagine that it said 2 times the natural log of x. How would I derive that? Yeah, exactly. You just leave the constant in front of the derivative, which is 1 over the natural log of a, and then what's the natural log of, or what's the derivative of the natural log of x? 1 over x, yeah. So if you squeeze that together, you get what they wrote up top, and we proved that it is true. I tried to do a product rule in there, that didn't work, just so you know. It's important to understand that a value. Okay. All right, so our last little example here. Now we're going to use which rule? So this time they say we're going to find the first derivative of 2. So specifically, we're looking for the slope when the x value is 2. Which rule am I going to use for number 8? Number 12. Okay, so we're looking at rule number 12. So we're going to have the derivative of the inside on the top. We're going to divide by the piece and then times the natural log of a. That's the one piece we add into this. So what's the derivative of x squared plus 1? 2x. So then I divide by that quantity. And then I also multiply by the natural log of what? A, which in this case is 2, the base value. Okay. So then, step 2 is now they want us to specifically look when the x value is 2. So what am I going to do? With the 2? Just plug it in. Yeah, plug it in. So we get 2 times 2 over 2 squared plus 1 times the natural log of 2. That's a lot of 2. So we get 4 over 5 natural logs of 2, which I would leave there because that is an exact form. That's it. Not too bad? Not too bad. I considered throwing 5, 6 at you at the same time because it's just the integral. It's like undoing it.